Welcome to the STEM Sessions podcast. I am Jarl Cody, your host and narrator. While reviewing outlines and in-work scripts for upcoming episodes, I noticed more than a couple of them rely on orders of magnitude in some capacity, be it part of a mathematical explanation or a means of sanity checking your thought process. So I figured it's worth dedicating a full episode to the concept on its own. Orders of magnitude is one of those scientific terms whose meaning in common lexicon diverges from its technical meaning. In this particular case, it's a dilution of meaning. I'm as guilty as anyone. In fact, I doubt I've ever used the term to its full meaning outside of technical discussions. I'm not sure if that's positive or negative, if I'm being frank. On one hand, the intent is correct. But on the other hand, should I feel badly for devaluing the term? Perhaps that's a question best left to historical linguists. This is the STEM Sessions Podcast, Episode 10, Orders of Magnitude. We frequently use the term orders of magnitude to compare quantities and qualities found in our daily lives. These comparisons range from the speeds of cars to the difficulties of homework assignments. For example, one may brag, "My Mustang is orders of magnitude faster than your Prius." Or a student may seek sympathy by declaring, "My fluid dynamics class is orders of magnitude harder than any other class this semester." Yet, despite how often it's invoked, the usage rarely reflects the term's full technical meaning. Yes, we correctly realize it means one quantity is much bigger or much smaller than another, but we rarely assign powers of 10 to the comparisons. This, I believe, can be partly attributed to our inability to conceptualize the scales that multiple orders of magnitude bring to the table. Let's look at a million and a billion, for example. Ask a random person to describe the difference between the two, and a common answer is likely to be a billion is bigger than a million. Perhaps a few will even answer a billion is 1,000 times larger than a million. But if you ask for a description or picture of the difference, you may not receive one because we don't have many examples in our daily lives from which to draw. In scientific notation, a million is 1 times 10 to the 6th power, which is a 1 followed by 6 zeros. And a billion is 1 times 10 to the 9th power, which is a 1 followed by 9 zeros. The delta between the two numbers is effectively the difference between the exponents, in this case a factor of 1 times 10 to the 3rd, which is a 1 followed by 3 zeros or 1,000. Thus, a billion is 1,000 times larger than a million. In terms of orders of magnitude, since 1,000 is 1 times 10 to the 3rd, and an order of magnitude is 10 to the 1st power, or 10, a billion is 3 orders of magnitude larger than a million. Yet, picturing 1,000 times increase in something can be difficult. To do so, we need to put the numbers in terms that are familiar to us. Let's use time as an example. 1 million seconds is approximately 11.5 days. 1 billion seconds is approximately 31.7 years. Not days, not months, years. When starting with a million seconds, a 1,000 times or 3 orders of magnitude increase is the difference between 2 weeks and 3 decades. Let's try distance next. 1 million inches is 15.8 miles or about 25.5 kilometers. 1 billion inches is 15,783 miles or about 25,400 kilometers. In other words, 1 million inches takes you from one side of Los Angeles, California to the other. But 1 billion inches? That takes you from Los Angeles to Perth, Australia, if you travel east, the long way around the planet. A million inches is the scale of a city. A billion inches is the scale of our planet. Let's use the same 3 orders of magnitude, but now we'll reduce the quantities. Starting at 1 million, a 3 orders of magnitude reduction results in a quantity of 1,000, or in scientific notation, 1 times 10 to the 3rd power. As stated earlier, 1 million seconds is 11.5 days. 1,000 seconds is 0.7 days. So the 3 orders of magnitude takes us from a week and a half to less than a day. And what about distance? Well, we know 1 million inches is 15.8 miles, but 1,000 inches is only 0.015 miles, or about 83 feet. So if 1 million inches takes you across a city like Los Angeles, 1,000 inches doesn't even get you to the end of the block. Revisiting the Mustang Prius comparison, a 2021 Mustang has top speeds of 155 to 186 miles per hour depending on the trim level. A 2021 Toyota Prius has a top speed of 112 miles an hour. If the Mustang was literally an order of magnitude faster than the Prius, its top speed would be a ridiculous 1,120 miles an hour. In reality, the Mustang isn't even twice as fast, with the Mustang Shelby GT500 being only 1.7 times faster than the Prius, a far cry from a 10 times increase. Those of us living along fault lines often experience a real-world example of orders of magnitude, yet we don't recognize it as such. This is the Richter scale for comparing the size of earthquakes. It's a logarithmic scale in which each whole number increase brings 10 times the amplitude and about 31 times the energy. So a 4.0 earthquake is 10 times bigger than a 3.0, a 5.0 10 times bigger than a 4, and a 6 10 times bigger than a 5. Thus, a 6.0 earthquake is 1,000 or 3 orders of magnitude bigger than a 3.0 earthquake. After experiencing a few earthquakes, you gain an understanding of this scaling. We often sleep through 3.0 earthquakes or mistake them for a truck driving by, but a 6.0 rocks you out of bed and damages structures and roads. Now, technically, the United States Geological Survey no longer uses the Richter scale, which is a local magnitude scale. It now uses a moment magnitude scale, but while the absolute numbers may diverge a bit from the traditional Richter scale, it's still logarithmic and the example still stands. Even though we understand the differences in earthquake sizes on paper, it's still difficult to assign a quantification to what we feel. Is that really what a 3 orders of magnitude increase feels like? How would I describe it so a person who has never felt an earthquake understands that too? This is because it's difficult to picture billions of something unless it can be translated into another something from our everyday experience. This makes us prone to both unintentional hyperbole and accidental understatements when attempting to put these concepts into words. This isn't due to a lack of education or critical thinking. It's just how our brains work. We simply struggle to understand extreme quantities, both large and small. Thank you for listening to the STEM Sessions podcast. This episode was researched, written, and produced by me, Jarl Cody. While I strive for completeness and accuracy, I encourage you to do your own research on the topic we discussed and confirm what I have presented. Corrections and additional information are always welcome. Show notes, contact information, and details of our other activities can be found on our website, thestemsessions.com. If you received value from this episode and wish to give some back, please visit thestemsessions.com/value for value for ways to support the podcast. Finally, please remember STEM is not the exclusive tool of experts, policymakers, or talking heads. Every presenter is susceptible to unconscious and sometimes deliberate bias, so always verify what you read and what you're told. Until the next one, stay curious.